geçsin. Bakalım. Şey oldu mu? Şurayı bir tekrarlayalım. Evet. Güzel. Tamamdır. Canlıdayız Oğuz. Herkese merhaba. Hoş geldiniz. İzmir Demokrasi Üniversitesi Yapay Zeka ve Veri Analitiği Uygulama Araştırma Merkezi'nin seminer serisi bu. Cuma günleri öğleden sonra yaptığımız seminer serisi. Burada hem akademiden ya da sektörden konusunda uzman, deneyimlerini de paylaşacak kişileri ağırlıyoruz ve temelde aslında tartışma konularımız ya da paylaşım yapma konularımız yapay zeka ve veri bilimi, veri analitiği, makine öğrenmesi, sinyal işleme, görüntü işleme ve bu tarz konular oluyor. Temelde teknoloji aslında. Teknoloji ve onların uygulanması üzerine konular oluyor. Bugün de yine benzer konularda bir konuşmamız olacak. Oğuz Vuruşkaner bizimle birlikte bugün. Hoş geldin Oğuz. Merhaba.
Hoş bulduk.
Davetimizi kırmadın. Teşekkür ediyoruz.
Size davet ettiğiniz teşekkür ederim.
Bugün şöyle güzel bir gün. Tabii bugün 23 Nisan. Hepimizin bayramı kutlu olsun. Tüm çocukların ve kendisini çocuk gibi hissedenlerin, çocuk ruhlu kalanların hepimizin bayramı kutlu olsun. Hakikaten önemli bir gün bugün. Şimdi şöyle güzel bir tarafı da var bugünün aslında. Bizim sanırım en genç katılımcımız Oğuz. En genç konuşmacımız olacak kendisi. Oğuz aslında hala ODTÜ'de 4. sınıf öğrencisi. Neredeyse mezun olacak. Ama yani aslında bir lisans öğrencisi ve oldukça da iyi işler çıkartan bir lisans öğrencisi. O yüzden de hem tanışmış olmaktan hem de davetimizi kabul etmiş olmasından çok memnunum. Şimdi kısa bir şey yapayım. Oğuz'un ve konuşmasının kısa bir tanıtımını yapalım. Konuşma İngilizce devam edecek daha sonrasında. Ama yine her seminerde olduğu gibi yapabilirsiniz. Başladı. Pardon tamam. Evet. Yine her seminerde olduğu gibi varsa sorularınızı yorum olarak yazabilirsiniz. Konuşmanın sonunda konuşmacımıza ileteceğiz. Şimdi kısa bir Oğuz'dan bahsedelim. Oğuz aslında dediğim gibi Orta Doğu Teknik Üniversitesi Bilgisayar Mühendisliği 4. sınıf öğrencisi. Herhalde bir aksilik olmazsa değil mi Oğuz? Yani bir pandemiyle ilgili bir sıkıntı da olmazsa bu Haziran-Temmuz gibi herhalde mezun olacaksın. Şimdiden başarılar. Şimdi şöyle güzel bir tarafı var. En genç konuşmacılarımızdan bir tanesi. Çünkü Oğuz aynı zamanda bir şirketin de ortağı. Yeni kurulmuş bir şirketin ortağı ICU diye Amerika'da kurulmuş 3 ortaklı bir şirket değil mi? Onun kurucu ortaklarından bir tanesi. Temelde aslında Edge Intelligence yani uç teknolojiler üzerine çalışıyorlar. IoT yani nesnelerin interneti odaklı ve oraya makine öğrenmesi, derin öğrenme yaklaşımlarının uygulanması, çeşitli sinyal işleme, sinyalini çok genel olarak kullanıyorum. Hani sinyal, görüntü, video hepsi dahil buna. Sinyal işleme uygulamalarının gerçekleştirilmesi ve bunun aslında anladığım kadarıyla birazcık daha netleşecek, yanlışım varsa da düzeltir konuşmasında. Anladığım kadarıyla bunun da embedded device'lara yani gömülü sistemlerde gerçek zamanlı real time çalışması üzerine odaklanmış durumdalar. Bu önemli bir nokta çünkü yani lisans seviyesinde daha lisans eğitimini tamamlamamışken şirket kurup sektöre atılan bu tarz bir maceraya atılan pek insan yok. O yüzden bence çok önemli bir atılım. O yüzden de tebrik ediyorum şimdiden ve yolunuz açık olsun da diyorum. Şirket olarak da hem senin için de. Bunun yanında Oğuz aynı zamanda CERN'de ML for Sim isimli Machine Learning for Simulation herhalde bunun açılımı. Öyle değil mi? O grupta da aynı zamanda gönüllü araştırmacı olarak çalışmakta. Yine pandemi tabii uzaktan çalışmayı da teşvik etti herkesi. Dolayısıyla orada da uzaktan o çalışma grubuna, yani CERN'ün o çalışma grubuna, ML for Sim çalışma grubuna temelde aslında derin öğrenme yaklaşımlarıyla çözümler sunmaya çalışıyor. Biraz daha recurrent, pekiştirmeli sinir ağları ile veri üretme üzerine anladığım kadarıyla. Şimdi bugünkü konuşmanın başlığı kısıtlı kaynaklı ortamlarda derin öğrenme. Abstract'ını falan zaten herkes biliyor afişlerden. Ben daha fazla detayını söylememe gerek yok. İstersen yapayım, kısa bir İngilizce tanıtayım seni, ondan sonra sözü sana vereyim. Olur mu?
Tamam.
So, okay. Welcome you all. Tabii ben kendimden hiç bahsetmedim. Devrim Ünay ben bu arada. Okay, so this is Devrim Ünay from İzmir Democracy University. So this is the again one of the seminars of the seminar series that we're holding at data analytics and then artificial intelligence applied and research center. So today is an important day. So it's the 23rd of April. So it's an important feast for us, national holiday. So I wish all of us a peaceful and a safe and sound, let's say, life and world. So yeah, today is important because we have Oğuz Vuruşkaner here. He's senior BS student at studying at METÜ, Middle East Technical University, Computer Engineering. And soon he will be graduating. But the important thing is actually he and two other friends of his have founded a technology company based in US, Maryland, I guess. The name of the company is ICU. So that's why that's important actually. He's one of the, Oğuz is actually the youngest speakers of our seminar series. And he will be explaining and sharing his probably some of companies' technological prospects and then aspects, and then what they want to do, what they want to achieve, and so on, and his view as well. Very briefly, what the company does is they are working on edge intelligence, and then they are applying it. So basically, as one of the technical guys in the company, Oğuz is actually leading the role of developing deep learning algorithms for real-time performance on embedded devices, specifically IoT-based devices. He's on the side, he's also a volunteer researcher at CERN in the machine learning for simulation group as well, where he's also contributing by data generation solutions using recurrent neural networks. So after this long introduction, I welcome you, Oğuz, and thank you very much for accepting our invitation. Again, you can share your content,
Okay.
and if our listeners have questions, they can type in. So the questions we will be answering at the end of the talk, I guess. So, floor is yours.
Thanks. Herkesin Ulusal Egemenlik ve Çocuk Bayramı kutlu olsun. Sunuma başlıyorum. Thanks for this introduction, Devrim Hoca. And here, as you see, we are working on limited resource environments, and I'm going to explain briefly what are they and why are we so obsessed with this word, limited resource. And here's an overview of my presentation. First, I'm going to introduce you this concept of limited resource environments, and there is another type of environment which also I'm going to introduce you. Then I'm going to give you an example of an improvement that can be made on the training stage, and then I'm going to give 2 examples of architectural improvements that model can be achieved better performance, better accuracy, and the future work that our deep learning, where our deep learning research is going, references and Q&A section. Let's get started. So, in economical perspective, with respect to econometricians, there is no such thing that its supply is unlimited. Always the supply is limited. At any point of time, you have a limited supply of something. And that's why, however, with respect to computational complexity or computational resource perspective, we might have something like virtually unlimited resources. Like if you need some more resources than you currently have, you might request this resource and you can continue your process with extra resources. And in that situation, you have a virtually unlimited resources. For example, to illustrate this kind of resources, data centers and cloud services are this kind of resources. You might improve, you can increase your resource usage. And also our training environments in deep learning are this kind of resources. Mostly, we can improve our usage of data or memory. Basically, we can improve our limits. On the other side, limited resources, they are, as it is called, they are limited. They are not extendable. For instance, perseverance in Mars is not extendable, does not have an extendable resources because it's out of our reach. Or for instance, embedded devices are also not extendable. Mobile phones are also practically, we can extend them, but practically they're not extendable. And that's why we have to adapt ourselves, our algorithms to these devices. And in our case, we are working on embedded devices and we have to adapt our algorithms for their resources, their limited resources. So basically, we can divide model improvements to 2 ways, two different subcategories, which first of them is training improvements. These improvements are made during the training, as I'm going to introduce some a technique which I'm going to introduce. Or we can improve our architecture, the model's architecture. By doing that, we will have better accuracy, or any given metric we are going to perform better results. And here's our benchmark data set. We are using this data set to examine our models and to compare between the models. And as you see, this model is currently a proprietary resource, but in the following months, we are going to release this public, and you can test the models, our proposals, and I don't know, you can try this anyway. And we have currently we have 4,200 training images and 672 validation images, which is enough for our experiments. So let's get started with training improvement techniques. First, here is this self-adversarial training. In its core, self-adversarial training is a direct attack to flows of the deep learning model, generally a classifier. You get information of the flow, the weak points of the deep learning model by using gradient vector. And in our experiments, we have used fast gradient sign method, as I referenced in this slide. And let us dive deep in the mathematics of fast gradient sign method, what it is and how can we achieve better performance And here is a simple mathematical formula. We have an X from our original data set. It is actually from SpaceX, one of the missions of the SpaceX. And when we take this image and just feed forward this image in the deep learning model, and then we calculate backpropagation, we get a gradient, which this gradient shows us a direction of by the definition of the gradient. When you have a gradient vector, you have the biggest change directions in a vectorized way. And by using that, you can detect flaws of the model. And this sign operation basically does, it just does whether the inputted number is positive or negative or zero. And by using that, we get the direction of the biggest flaw in the gradient. And by multiplying it with a small value of epsilon and adding it with our original data, we might get a significantly different output, misclassification error with high confidence. And by using this technique, we might reduce the false positives or misclassifications error significantly because of that. It is a self-evolving data augmentation technique, and I'm going to show you our experiments with this technique. As you see, in our case, the correct alarm means you give a correct alarm, like there's a fire in the image. And false alarm means there is no fire image, but you still give an alarm. And in this results, the 0.1% does not do well. I mean, it is not a great increment in the performance, but when it comes to false alarm, 10% decrement in the false alarm is a huge success. You're eliminating 10% of the unnecessary, false alarms, and this is a huge improvement. And by adding only one step to your training, using an adversarial backpropagation and then recalculate forward propagation and then calculate your loss, you get a 10% increment in decrement in false positives. And to conclude this section, false gradient sign method is a valid data augmentation strategy. Since you calculate this every time in every training loop, this data augmentation strategy is being updated by our deep learning model's state. And that means it is, for instance, let us compare this with static data augmentation methods like flipping the image or cropping the image. They are not adaptable to models' current state, but this algorithm provides us an evolving. This algorithm provides us this. When the model updates, this algorithm also updates the flows, and we get with respect to this algorithm, the best flow. And here it comes, the architectural improvements that we can make by only adding a layer or diminishing some layers or simply changing data types. We might get architectural improvements. Let's start with model quantization. Quantization in signal processing is a way to convert analog signal to digital signal. By doing that, you can get input from the nature itself, and you can process it in our computers, our binary systems. In this case, in this context, model quantization, it does the same thing. We get a float value and we convert it to an unsigned integer or integer value, which has a smaller bytes with respect to float value. For instance, a standard for floating point is standard floating points have 4 bytes. They require 4 bytes for storage, but 1 byte requires 1 byte. And if you convert this 4 byte value to 1 byte value without losing that much precision, you have a huge improvement on the model's memory usage. And it is crucial in our embedded systems because we desperately need memory, since our memory is one of our restrictions, our most crucial restriction. This technique really improves the performance and improves the performance crucially. And I'm going to introduce you some other concepts, which is subconcept of quantization, and one of them is quantization schema. This is the formal definition of translation between data types. As I told earlier, you translate a float value to an integer value. To do that, you have to define something formal, and this is what we call quantization schema. And another thing, while training the models are trained with, deep learning models are generally trained with floating point or double values. You do not train them with short floating points, which are 2 byte floating point values or integers. And to handle the precision errors consequence because of the following quantization, you use quantization aware training, which translates values, floating point values to integer values continuously throughout the training. And here's an example quantization schema. To declare a quantization schema, we first define an interval which quantization calculations are going to be made. We call this interval as quantization interval. And as you see here, there's a function we have assigned, we have created, which is called clamp. Clamp function translates outlier values to this line segment as we have defined. And quantization step is the one step of when we at the next slide you are going to see this better. And here's a quantization levels formula. Let me continue with an example quantization. So here we have defined a quantization interval starting from minus 3.048 to 3.048. And there are 255 different quantization steps, and that gives us this translation. Minus 3.48 goes to minus 217, which is the smallest value on the byte, on an integer byte. And minus 2 goes to minus 83. But the most important thing you have noticed is that 4 goes to 127. That's because we translate this 4 value to 3.0.48. That clamp function, that is what clamp function does. Clamp function translates outlier values to this desired interval and then recalculate these values by thresholds. If the value is above the threshold or below the lower threshold. And here's the results of our training with quantization. Quantization, it is important to protect the accuracy values by quantizing. Unless if you decrease the accuracy, you might get bad results and you don't want to quantize this model. But in this case, the model can be quantizable because you don't lose that much accuracy and that much false positive rate. And the significant thing in quantization, you don't, if you protect the accuracy values, you are going to get a smaller resource usage values. Let us interpret these graphs. First of all, this gray blocks tell us the floating points time intervals. By the way, we have experimented with 100 inferences, and these calculations are made by 100. As you see, in one batch size inference, quantized model has better inference time. That's important. That's what we want. Also, that's what we expected from this situation. And as you see, again, there are no crucial differences between them. But again, we can say that quantized model outperforming at batch size 4. But there are something crazy is happening. As you see, the quantized values inference speeds they tend to become more volatile than the floating point when you increase the batch size. This means the consistency of the quantization underlying quantization implementation is not consistent, and that might be a problem. The inference, as you see, the inferences are varying too much, and in the high batch size situations, you might not want to quantize your model, and you might you might continue with your floating point model. But I think that these improvements, this consistency, are going to be provided in the following days of this development of the deep learning libraries. To conclude, in the lower sized batch inferences, quantized inference outperforms normal inferences. However, in the increasing batch sizes, you cannot get that performance, that speed up, and that's because of the inconsistency of the implementation over the hardware. And finally, I'm going to talk about stepwise separable convolutions. This technique is extensively used on mobile nets, and actually this is an really well. If you let me just tell you what it is, and so here, as you see, this is a naïve convolution operation. You get a unique kernel for every input-output filter pair. But in stepwise separable convolution, you get a single kernel. Pardon me. If you have 2 dimensions, you get 2 kernels for every input or input-output filter, and this is actually a m times smaller kernel parameters. And again, if you in this, that's the stepwise convolution. That's what stepwise convolution means. You assign a kernel to every input filter. And here's what separable convolution does. Separable convolutions convert n-dimensional input kernel to n many one-dimensional kernels, and then you sequentially calculate the values, and you get a fake pseudo kernel calculation, and you have a diminished amount of parameters, and that's an efficient way of decreasing parameters. But as you will see, the results are not that great. Here's a memory complexity of naïve convolution. As you see, kernel square and m square is gone at the stepwise separable convolution, and that's what this technique provides us. And we have used this in our experiments to unsupervised anomaly detection on real-time streams. To improve the speed we have used this technique to decrease model size, and as we will see, the learning is performed well, but the speed isn't provided that well. And here's an example of a hourglass network architecture, which we have used in unsupervised anomaly detection, trying to construct the input value using a decoder network. Actually, this network is also called autoencoder, and I don't know. Hourglasses are also, hourglasses and autoencoders, they are both valid names for this network. So let's first look at the naïve convolution unsupervised anomaly detection model's outputs. The expected output is bounding boxes where the anomalous frame happened. As you will see, we are performed well in this experiment. To achieve these bounding boxes, the deep learning model has been trained with normal frames. Like this can be counted as normal frame. There is no explosion happening, and it tries to learn the environment, the background, and when something unexpected comes into frame, it just detects it and bound box it. And here's the depth-wise separable convolution, which you can see has a real improvement with respect to parameters. With the multiplier of 6, about 6 times lower parameters than the naïve convolution. Again, the anomaly is detected, and it is working fine in this situation. However, what we have expected is inference time of the depth-wise separable convolution should be lower than the naïve convolution, and I don't know, as I'm going to explain later in the conclusion, this might be happened because of the adding of this performance, expected performance cannot be performed because of adding 2 extra layers, that separable convolution layers, and because of that, the average inference time has increased with respect to naïve convolution. So real-time anomaly detection with self-trained models are still active research field, and we cannot conclude this research, but we are approaching to that point. I have our future map. At the future, we might solve this problem. I have future work about the deep learning techniques, and currently we are developing models accounting these techniques, like student-teacher models, the knowledge distillation. These are crucial techniques on improving performance on the training phase, and also pseudo-labels. Pseudo-labels are also good if you have a limited amount of data that is labeled, and you train your unlabeled data with your labeled data, and you get better performances than training only with labeled data. And confident learning, which improves dataset qualities, the labeled dataset qualities, and also meta pseudo-labels, a combination of pseudo-labels and student-teacher models are work on the deep learning sides like this. And here's the references of my presentation. Thank you all for listening to me. I would love to answer your questions.
Great. Thank you. It was a very a very short and condensed presentation, actually. So it was full of important observations, some experimental results, and so on. Great. Thank you. So there are a few. Well, there is one message from Ege Nerse. Yeah. Okay. So he says thank you, Oğuz hocam. So it was a nice compliment. So well, I have a few questions. I can ask a few questions, but do you want us to continue in English or in Turkish, whatever you like?
You can continue English.
English, okay. So there were three main contributions in your talk, and then, but the first thing is, in the beginning you said about a data set, right? Fire detection data set, and then you said that soon. Currently, it's not released, but soon it will be publicly available, so it will be freely open to researchers. Could you give us more information about that database? So, is it, for example, is it just a database of images, or does it contain videos as well? Because I understand that it has. I assume that it has two classes, so data with fire or data without fire, I guess. But I'm not sure. So can you give us more information about that?
Of course. It contains only images of fire and smoke. We are trying to benchmark using only fire labels. However, we also have labeled smoke images.
Okay. Then is it like label per image, or do you have segmentations or bounding boxes and so on?
Label per image.
Label
if
per image.
If it contains smoke, then it is a smoke image. If it contains fire, it is a fire image.
Oh, nice. And this is a data set that you collected as a company?
Yes.
Or okay, interesting. So maybe so Başak Hoca also thanks for the presentation. Maybe you can actually say a few words about the company, your company actually, ICU, and the relationship between the content that you shared and the company. So because I made a brief introduction about the company in the beginning, but probably our audience does not know much. So yeah.
Okay. We are basically trying to improve the performance of deep learning models on the embedded devices. For that reason, we have to research deeply on the model performances and accuracy. Without losing the model's accuracy, we have to improve speed and memory usage, memory performance of the models. And for that reason, as you see, this presentation is like a survey, academical survey about these techniques, improvements that can be done, and that's actually a 4-month long academical survey of what we have done and what we are going to do in the context of deep learning. We also contributing in the field of intelligence and networking. Pardon me. We also have contributions and research surveys on networking, basic networking and complex networking stuff. And this is the deep neural networks side of our let's say know-how.
I understand. What I understand is that you're really, as company, you're really focusing on memory efficient solutions, memory efficient deep learning solutions, signal processing solutions, image processing solutions, and so on. And that's why I guess the presentation, in your presentation, you were really emphasizing memory efficiency, decreasing the number of parameters by that quantization approach, and so on. So that was why it was the focus, I guess. So this is like you're trying to generate some nice solutions based on some simple models, or make
Yes.
simple models, and then you will try to deploy them to embedded devices where you will have limited resource, right?
Yes.
So,
That's the point.
so currently, did you try to deploy any model in this in any kind of limited resource environment, like an embedded device? Is it working? Do you have a demo or anything like that?
We have currently deployed our models and trained different techniques, models on this limited resource environments, not constraining ourselves with limitless environments.
Yeah. Okay.
Yes.
Yeah. So yeah, that's what I was asking actually. So as a company, obviously you're working on the embedded devices, so you will be releasing those devices soon. But yeah, you're also working on that. So your main concern is that limited resource environments and how you can achieve the top-notch performances
Yes.
with less parameters, with smaller models, less number of annotated data, and so on.
Yes.
Yeah, interesting. The quantization part was interesting. The first part was also interesting, actually. In the quantization part, again, many of us researchers are, let's say, especially from the researchers from the academia, we are not really into the data types and how they affect our models and our full solution. And it was interesting in the sense that even just the selection of quantized numerical values, then floats, for example, could make so much difference in terms of the speed and probably in terms of memory as well, memory consumption as well. Because I think you did not present any memory consumption related performance result, but I guess you saw some improvements there as well. Did you?
Yes, we have seen performance improvements on memory, but our main focus on this quantization is about speed. We have to speed up the model's performance, model's inference speed, and that's why we didn't observe that much on memory. By the way, this is the engineering part of the deep learning. The deep learning has also an academical research part, and really it can be counted as hard optimizing the models on the predefined hardwares, which is the engineering part of the deep learning.
So there are actually two questions coming. So as we continue to discuss, as audience digests what you have presented, actually, because as I said, it was very, very condensed presentation. So questions come up. So Kemal Hoca from our university, Kemal Hoca is asking, I'll show it actually. Is there any realization on embedded systems of your deep learning algorithms besides implementation? So yeah, it's something related to what I asked. But yeah, because Kemal Hoca is also very, very much interested and related on implementation or realization on embedded systems, because his expertise is on that side as well. So what do you think?
We are not only engineering deep learning models, but also we are doing a network engineering, using networks in the most effective way. That's why we have done such realizations.
Okay, so yeah. So the answer is yes, there are realizations, but more will come soon from the company side, right? So there is also one additional question. First, a thank from Borahan Tümer, and then for the nice presentation. And then Borahan Tümer asks, or has a suggestion actually, could you maybe formally define anomaly to give a good insight about the context of the target system that you are focusing on.
Yeah. Well, yes. In our context, the anomaly can be defined as, well, when you look at the street, you're not an explosion is an anomaly, because in normal situations people can walk, cars are passing away, but there are no explosions occurring, and that's actually that is not defined by us. This is the machines learning stuff of the. Model is learning the anomaly with respect to its data. Data is streaming to the model, and I think that's the answer.
I understand. So in this context, then, while I was watching the videos that you showed, I was just thinking, the anomalies that you have recorded, are they real, or were they injected, let's say, into the video? So were they synthetically created or real videos?
No, these videos are taken from a public data set, anomaly detection data set. These videos are real. These explosions are real. Yes.
Okay. Interesting. Would this, well, if, an interesting, I was interested in the following. Would this, for example, would your solution work in the case where we can define anomaly as in a biology environment setting where cells are sometimes randomly exploding, for example? So it's kind of an explosion, but there is no color, but these are different shaped cells, and then from time to time some of them just explode. Would it work in that scenario?
Well, in this model, model is trying to compares pixels with respect to learned representations, and that's a pixelized comparison. And if there are some contextual differences, the model can not detect this because pixelized things might seem correct, but as a general picture, in the general picture, the anomaly can be occurring. And this is I cannot answer this question, but yes or no. Yes.
Probably. Well, I was asking, while I was asking, I was thinking actually probably it would work, or if you kind of do a transfer learning and then retrain with a short amount of video data from the biology lab where you have such information, so it could maybe work. Regarding, again, anomaly, actually Borhan Tümer actually follows it up. He says, I'm just going to show it. Is any change in the image an anomaly? Nice question. That's tough to answer. Yeah.
There are two very similar problems. Which one of them is novelty detection and one of them anomaly detection? In novelty detection, the change in an image, but meaningful change in an image, is an novelty. But in anomaly case, people's walking, again, a distinct example, people are walking in the street, people are walking in the street, and they are not the anomalies, they are people. It's a normal thing. But an explosion is an anomaly in this case.
So we can maybe define anomaly as something occurring rarely in the image or in the video sequence, right? So if let's say in 50, 60, 70% of the video people are walking, and then for some small amount of frames there's a dog, it could be an anomaly. Or there's an explosion, it could be an anomaly.
Yes.
Right. So it's a tough term to define. I understand.
Even for people, yes.
Yeah. I'm just checking if there is any more question. Currently, none. I have no more. I had one question from the first part, but I forgot that. I don't remember now. But thank you very much. This was interesting, an interesting talk. Great. It was very to the point with very clear technical purposes and clear aim actually. Hopefully you will have great products coming out soon, and it's a by the way, it's a very nice initiative to be releasing, to have taken the decision of releasing the data freely, that will be freely available by the company, by your company actually, that fire detection data sets, if I'm not wrong, the name. So that's also very nice, because we don't see much about this kind of contribution from companies. Big tech companies do this because they have the resources, they have the manpower, they want to do some they want to be known by that data as well. But especially relatively small startup companies like ICU, this is a very nice initiative. Well done. Congrats.
We believe this open source movement, and by sharing this, this is not only for actual contribution to open source. This is companies can do this also for native advertising, and and we believe this will be good for us, and well, we will see.
Okay, so maybe a few last words. By the way, Boran Tümer says thanks for the answers. He thanks me as well, so thank you, Boran Bey. Kemal Hoca also says thanks for the presentation, and he wishes good luck on your way. Maybe before we conclude, I would like to get a few comments from you about founding a company at this very early age in another country with two of your friends, colleagues. I don't know how I can name. So, what would be your comments about that? So, what would you suggest? What would you advise? What were the good parts, difficult parts, and the very motivating parts? I know that it's very early. You're very at the very beginning, but still, you may have some insight.
Well, people should do this at their early ages. But people also get successful at the later startups. But you learn too many things by doing something unique, by founding a startup. You might not learn this by working on a pre-founded company. There are some things that you can only learn by founding a startup. I believe in that, and that's why I'm trying to found a startup with my team. Salute to my team, by the way.
Yeah, salute to them as well. Okay, great. Thank you very much. I guess no more questions. Again, Erse says yolunuz açık olsun. And I second that. Yolunuz açık olsun. Thanks for the nice presentation. Thanks for the time.
Thank you too.
And good luck with all the coming up adventures and the graduation, the company, and everything. Okay.
Thank you.
Okay. Bye bye.